This video is about logarithms. It corresponds to sections 2.3.1 and 2.3.2 of the Applied Analog Electronics textbook. Now, the definition of a logarithm is fairly simple. It comes from sort of turning around the equation for exponentiation. So if we have e to the x equals y, we can write that relationship as the natural log of y is x. Similarly, if we have 10 to the x equals y, we can write that as log base 10 of y equals x, and 2 to the x equals y is log base 2 of y equals x. And when you're writing a logarithm, always do put in the base here, or use natural logarithms, because though there is a convention that if you leave the base out, it means you use base 10, that's not always what you meant. And so by being always explicit about it, you reduce confusion on the part of the reader. All right, what are the properties of logarithms? Why do we bother with them? Well, again, these things come from properties of exponentiation. If we have e to the x times e to the y, that's equal to e to the x plus y. Another way of saying that is that if we have the natural log of a times b, that's equal to the natural log of a plus the natural log of b. And that means that if we want to do a multiplication of two numbers, if we're working in logarithmic space, we just have to do addition. And historically, this was one of the main advantages of logarithms, because addition is something that people can do manually fairly easily. Multiplication is much harder to do manually. So before the days of calculators, a big use of logarithms was this to turn multiplications into additions. And of course, the same thing happens with division, because if we do e to the x divided by e to the y, that's e to the x minus y. So the natural log of a over b is natural log of a minus natural log of b. Sort of a simple consequence of that, e to the 0 is 1, and so natural log of 1 is 0. E to the minus y is 1 over e to the y, so minus the natural log of a is the natural log of 1 over a. What else we got? Oh, differentiation. We have differentiating e to the x with respect to x is just e to the x. And if we differentiate the natural log of a with respect to a, we just get 1 over a. Okay. The ones up here before the differentiation one were all ones that would apply to any sort of logarithm. It doesn't matter what the base is. The special properties for differentiation only work with e to the x and natural log of x. But of course, you can convert between different base logarithms just by using that e to the natural log of 2 is 2. So e to the natural log of 2 times x is 2 to the x. And if we take you can turn this around into identities on logarithms also. One other identity that's worth knowing about, e to the epsilon for a very small epsilon is approximately 1 plus epsilon. And that means that the natural log of 1 plus epsilon is approximately epsilon. And that's a very good, very useful approximation that you can use often for back-of-the-envelope calculations, where you don't want to pull out a calculator and get an exact number, and you just want to know, oh, it's going to be about the natural log of 1.07. Okay, that's about 0.07, and you don't have to go through a lot of work to make rough approximations. All right, that's a bunch of properties of logarithms, and I'm hoping you have seen these before, because that's not enough practice really to know what you're doing with logarithms. But what do we use logarithms for in engineering? And there are several places we use them. Usually it's to deal with ratios of things. And one ratio that we look at a lot is something called gain or sensitivity. Gain and sensitivity are basically the same concept. They're both how much does the output change with respect to the input of some system. And the difference between the two is that gain, we're usually talking about an amplifier, and usually with an amplifier where the output and the input are in the same units. So it might be input volts, output volts. So the change in output voltage with respect to the input voltage would be the gain, and that is unitless because it's volts per volt. Sensitivity is usually used for sensors, and there your inputs and your outputs are usually in different units. So for instance, if we're measuring pressure, the inputs in pascals, the outputs in maybe volts, and so we're looking at volts per pascal as the sensitivity. All right, why does this get into ratios? Well, for gain, obviously, volts over volts is a simple ratio, but we can do this same concept of ratios, and we often have to multiply gains and sensitivities. If we've got a sensor that gives you so many volts per pascal at its output, then we put that through an amplifier, which gives me so many volts per volt as its gain. We end up having to multiply the sensitivity times the gain, and we might have an amplifier that has several gain stages. And doing all that multiplication, I mean, it's not too difficult with calculators, but sometimes you end up with lots of zeros, lots of things getting bigger and smaller. And so it's very common to express these different things all in terms of logarithms, because the gains are all ratios. The sensitivity is really a ratio, but it's not unitless. So we can't really take a log of it unless it's unitless. Remember, from dimensional analysis, you can only take logs of things that are unitless. So sensitivity is usually expressed in terms of a ratio relative to some fixed amount. For instance, we might talk about the output in volts per pascal, or the output over the input in volts per pascal relative to 1 volt per pascal. So that we can now take the log of that and end up with a unitless thing here that we can take the logarithm of. When we're doing this, engineers like to use not log base 10, but a different unit, 20 times log base 10, which is equivalent to using like 10 to the 1/20th as the base. This 20 log base 10 of an amplitude ratio is known as decibels and abbreviated with dB. And a lot of times the sensitivity of sensors and the gain of amplifiers are expressed in decibels. For gain, decibels, because it's inherently unitless, it's just output over input, or change in output over change in input to be more precise. You can get something there that's just, you know, I got 20 dB gain here, I got 10 dB gain here. 20 dB is a gain of 10. 40 dB is a gain of 100. 60 dB, gain of 1,000. So you can take the sensitivity, maybe it's expressed as, oh, this has got sensitivity of minus 47 dB relative to 1 volt per pascal. And then you say, okay, well, if I do 20 dB in the first stage, 20 dB in the next stage, and 20 dB in the third stage, you can say minus 47 plus 20 plus 20 plus 20, and that's what 60 minus 47 is 13. And say, okay, I've got a total sensitivity of 13 dB, and I can do that addition and stuff in my head, even if the numbers are not nice round numbers here. Multiplying things that aren't round numbers is much harder to do in your head. So engineers have gotten into the habit of expressing a lot of things like gain and sensitivity in terms of decibels. Now there are other units that sometimes get used. Sometimes people use just log base 10, and then they often talk about things in decades. That's particularly done for things like frequency ratios. So if you say from 10 hertz to 100 hertz, that's 1 decade, a factor of 10. From 10 hertz to a kilohertz, that's 2 decades, a factor of 100. And so quite often, log base 10, if you're just doing that, people talk about decades. You'll also see a lot of log base 2 used. And when you're talking about that, particularly in terms of frequency, log base 2, there the steps are octaves. 1 octave is a ratio of 2 in frequency, 2 octaves is a ratio of 4 in frequency, 3 octaves is a ratio of 8 in frequency, and so forth. And so quite often you will see people referring to how many decades, how many octaves something is. And these get used particularly for frequency, but also sometimes for other units. A lot of what we use logarithms for are also to express wide ranges of values on a single plot, particularly where the ratio of numbers is important rather than differences between numbers being important. And we'll talk more about the various sorts of logarithmic plots we use in a subsequent video.